lecture is going to be the last lecture of this course. I'm going to be mainly talking about two things, which are linear regression and correlation. Actually, correlation is going to be the topic that I haven't covered in the previous years, but I guess from starting from this year, I plan to include it within the curriculum. It is the basic idea, that the fundamental reason for that is because of the coronavirus incident. Actually, people have been showing and people have been seeing the correlation graphs or the figures between two variables, two random variables, very frequently in their daily lives, in newspapers, on the websites. So I would like to give a little bit more information about those, about that topic within the context of correlation. And the first topic is going to be linear regression. But before that, in this lecture, I'm going to be only talking about the concept of statistical modeling. And when I have to talk about statistical modeling, I have to also talk about mechanistic modeling. So that it's going to be a comparison between those two. So that's why I put the zeroth subtopic as mechanistic versus empirical modeling. So this is going to be a kind of overview of the types of model that you have covered in other chemical engineering courses versus the types of model that we are going to be covering as an example as a linear regression model. And I'll try to also connect the statistical modeling concept to the things that we have covered in the second part of this course, which are related with the statistical tests and those concepts. Anyway, so what is mechanistic and empirical modeling, and what do they have got to do with it's simple linear regression? Let's see. So what we call mechanistic modeling is actually using fundamental, they are also called natural and constitutive laws. And if you use a combination of these rules or laws to come up with a mathematical model of a process, of an event, of a natural phenomenon, then that endeavor, which is that modeling exercise, is called mechanistic modeling. Actually, I'm going to talk about what fundamental and modeling of fundamental laws and constitutive laws in a minute. Mechanistic models are mostly deterministic because actually the idea here in mechanistic models, the general philosophy is to dissect each part of a whole as a separate unit, then connect them together and come up with an explanation. That's usually the work that, let's say, the classical view of the science. So when it comes to that, since we are trying to explain the individual parts, and you can actually dissect reaching to the smallest part, and so each of these small parts are assumed to follow natural laws, and actually natural laws, except quantum mechanics, are deterministic natural laws. So the mechanistic models are usually seen as the deterministic laws. The very typical examples are that I'm going to talking about, for instance, Newton's laws, Newton's law of motion. So, or the very simple Newton's law of F is equal to mass times acceleration. There is no statistical element there. There is no variation or anything like that. So it's just if you determine the two of the variables in that equation, the third variable is with no error, it is determined. So it's there is no statistical component there. So the fundamental laws, what do I mean by fundamental laws, which comprise one aspect of mechanistic modeling? Well, actually, maybe if we can list a couple of those in our courses that we have seen in our courses, it's going to be easier to understand. For instance, conservation of mass, which you have seen mass and energy balances and fluid mechanics course. Conservation of energy, the very same two topics you have seen in those courses. Actually, conservation of energy is also a topic you should have seen in a physical chemistry course. You should have used them, yes, if I recall correctly. So I should have added here. Now, when it comes to momentum, actually as far as I know, you do not cover or you didn't cover angular momentum in fluid mechanics, or maybe if you did, I'm sorry for that. But surely you have covered linear momentum, and actually that's how you come up with the relations of pressure loss with respect to velocity relations. So with delta P is going to be a function of, call that function with some parameters here, alpha, and it's going to be a function of fluid velocity, or the average fluid velocity, or fluid flow rate, call it like that, if the Reynolds number is in the laminar flow regime. And then delta P is equal to that, again, some alpha prime, call it some with different parameters, f squared. This relation is assumed to be valid when Reynolds number is greater than this value. And this relation, when we have laminar flow, not the turbulent flow, this relation is determined from fundamental laws. But it's not only the fundamental laws that we use here. It's not only the momentum laws, but there is also the equation which relates stress to strain. For instance, those equations are what we call constitutive equations. The constitutive equations involve relations specific to the phenomena under study. So they are not as much general as conservation of mass. Unless we are talking about a nuclear reaction, mass is assumed to be universally conserved from the atomic scale to the stars and planets, all the largest scale. And when it comes to conservation of energy and momentum, it's the very same thing here. On the other hand, when we are talking about each, or not, it's not going to be the whole universe that we are interested in. We are going to be interested in a certain type of phenomena. Then the equations that we usually use are what we call constitutive equations. So what are these constitutive equations? It's going to be clear in a minute. Those constitutive equations usually come from two sources. One of them may be using these fundamental laws, but with some certain assumptions depending on the phenomena under study. So we obtain some constitutive laws. Now, those assumptions, actually, those simplifying assumptions, will prevent this constitutive relation to be as much applicable as a conservation law, because those, as it says, some simplifying assumption, actually we aim to simplify. However, we make some constraining assumptions. I think that the very typical case that you are already familiar with, even from high school, is ideal gas equation. Ideal gas equation is not a fundamental law. Actually, van der Waals gas equation, or any state equation, none of them is a fundamental law. They are all constitutive laws or constitutive equations. We have some equations of states which work for some gases. So they are specific to the phenomena. And some of these equations, I'm not sure whether all of them can be derived, but for instance, ideal gas equation can indeed be derived using Newton's mechanics. Then you make some simplifying assumptions, like each of the molecules not interacting with each other, and then you can come up with the ideal gas equation. Historically, I'm not sure about that. If anyone is interested, I recommend you to have a look at that. I guess ideal gas equation was first experimentally determined. So it was not derived using the fundamental laws, I guess. It was what we are going to talk about next as the phenomenological equation, which was obtained just to explain the experiment. But later, I think that was derived, but I'm not sure of that. But a very typical case, maybe, which fits the story, and I know that this fits the story, is the Newton's law of cooling. Newton's law of cooling, with chemical engineers know it also as the force convection equation. So equation which we are going to be covering in this term in heat transfer course. So Q is going to be, the heat transfer is going to be equal to some heat transfer constant, some area times temperature difference between two surfaces. So this is going to be our convection, heat transfer due to convection. that delta E is going to be the bulk temperature, the difference between a liquid surface. Let's say this is going to be the metal region here, and we have a liquid here, and the bulk surface temperature, bulk region temperature is here, T bulk, and this is T steel or T wall, call it anything that you like. Delta T is going to be equal to T wall minus T bulk, or whichever you define, whichever is the hotter region, and then you multiply with the surface area and the heat transfer coefficient. Anyway, this is what we call Newton's law of cooling, and the way that Newton uses actually what we're going to be calling phenomenological equation. Let me put it that way: phenomenological model. So this one is just used to explain the experiment at hand. It's not inconsistent with the fundamental theory, but it is not derived by that, or it's not derived from that. But after Newton has been using this law of cooling, I think Stefan Boltzmann equation, which are derived or which are obtained from statistical mechanics, actually is from simplifying the Stefan Boltzmann radiation equations, you can come up with this relation. So what I'm trying to say is that those constitutive equations may either be obtained as phenomenological models, which are but not derived for it. They are just used to explain the experiment, or they may be derived using some assumptions on fundamental laws. What are some other constitutive relations of this form? For instance, rate equations. Again, rate equations might just be applicable for the reaction at hand, so it may be thought about a phenomenological model, or it may be derived using collusion theory. But actually, there are going to be, I guess, limits to that for certain reactions with heterogeneous systems, right? With absorbance and the molecules and desorption of the molecules, all these stuff. Then I think I'm not actually into catalyst, but as far as I know, the constitutive equations used cannot be obtained all from fundamental laws by using even using some simplifying assumptions. We are going to be using sooner or later phenomenological models to come up with the all model parameters. Well, but the typical phenomenological model that you have seen, for instance, in fluid mechanics, is the Fanning friction factor. For instance, I guess for Fanning friction factor, which is a parameter or a constant used to determine the friction employed or felt by a fluid flowing inside or moving inside a pipe, when our Reynolds number is above the laminar range, but it's not a very, very high turbulent flow. So when it's in this range, that Fanning friction factor is usually used, and it works. Note that this cannot be derived from by some fundamental laws. Maybe in the future that would be possible. I don't know. It depends on how much the fundamental laws and the constitutive equations which are obtained, which are derived from these fundamental laws, how much they are powerful and how much they are various. But actually, still, this is going to be used to explain a specific phenomena or a specific observation from an experiment, and it's going to work actually for a certain Reynolds number region. This equation, people have found that this equation works, and this is actually what I call a phenomenological model, which is, as you have realized, pretty much difficult to pronounce. Anyway, so these are what we call mechanistic models, and please, that would be actually an interesting exercise. Think about the other courses you have taken and you are currently taking, and think about the equations, all the equations in those courses, and see, well, they are going to be, as far as I'm concerned, all the equations that you have seen and you are going to be seeing in the chemical engineering curriculums are going to be mechanistic models, but try to relate them to whether they are obtained, they are fundamental laws, or they are constitutive equations. For instance, a very simple equation in a pipe. This is area 1, this is area 2. Let's say that the areas are slightly different. So let this be like this. Then we write this relation. Velocity times area 1 is going to be equal to, let me draw this matter. Yeah. Area 1 cross-sectional area 2, and a liquid is flowing, and we use this relation. So is this equation, is this model, actually, is this a fundamental law or is this a constitutive equation? Actually, it's a fundamental law, and you should then, in this case, you should show it. Well, in a way, it may be used as I also thought about a constitutive equation, but I think no, because the assumption that we make is not a simplifying assumption, but it is very much related to the phenomena at hand. So this is actually at steady state, what comes in will go out, and this is actually represented by this equation. Because this is actually mass flow rate at point 1 is going to be equal to mass flow rate at point 2 at steady state. So this is basically application of conservation of mass at steady state, mass flow rate, which is equal to density of 1, velocity, and area 1. Now, assuming that this is an incompressible fluid, densities will cancel with each other, right? And we are going to be left with this equation. So this is not a novel equation out of nowhere. An additional equation is going to be a fundamental law application of conservation of mass. Think about other equations that you have seen and you are currently seeing in your courses right now. So try to classify them into those type of equations. Anyway, now the second type of modeling, and the type of modeling which you have not seen in any of the courses you have taken in chemical engineering curriculum, is what we call empirical modeling. As the name suggests, empirical modeling actually it's related with experience and experiment itself. We are not usually interested in general laws. We just want to come up with a model, with an equation which explains the natural phenomena at hand. And for this purpose, when we use statistical models, and actually we can use statistical models between statistical relations between measured variables. In statistical models, constraints offered by natural laws are generally not taken into consideration. Now, when I say it in that way, it seems to be quite possibly at first sight, empirical modeling is similar to phenomenological models, which comprise the constitutive equations. Actually, they are not going to be equal to each other, as I'm going to show you in a minute. But to construct a statistical model, we require the following three objects: a set of statistical or experimental units, which are actually experiments; regressor, or what we call predictor variables; and also response variable. I'll talk about what these are in a couple of minutes. But before that, I'd like to give an example from the literature. From this paper, I'm going to be showing you now. So this is a paper published in Industrial and Engineering Chemistry Research Journal in 2006. And the title of the paper is Comparison Between Phenomenological and Empirical Models for Gas Phase Polymerization Process Control. Well, gas phase polymerization process is actually a chemical engineering process. So this paper is about a comparison of two different types of models, which are empirical, which are going to be statistical models, and what we call phenomenological models. So let's directly see what they are. First, the phenomenological models. This is, as you can see, a scheme of the polymerization process model. It starts here. This actually, there is mass balance here. Yeah, the reactor, right? This is a fundamental law. Now, in reaction rates, these are going to be constitutive equations. Reaction rates are usually themselves, as I said, they are, although some simple ones can be derived from collusion theory, these the parameters in the reaction rates, the order of the reaction rates, they are actually they make the reaction rate equations phenomenological equations. And actually, we have all these descriptions of the polymers, right? Monomer, potential site, active site, dead site, all of these. And all right, there are all these equations. And now we have, as you can more clearly see, maybe you are more familiar with those kind of equations from the Reynolds number and the viscosity and density, all these relations from fluid mechanics course. So you can see many phenomenological relations here. You can also, as I've shown you, also we had some fundamental rules, but as a whole, this whole set of many equations try to describe a single process. Of course, as I said, it also consists of some equations, general equations, like conservation of mass, maybe probably conservation of energy, but also it consists of many phenomenological models or equations here. So this is as a whole consists of a phenomenological model. On the other hand, what we call an empirical model is actually very straightforward. In empirical modeling, we do not care about what's going on mechanistically. We do not care about those details, polymer formation, the change, the growth of the polymer, the depth of the polymer, and the reaction rates. We do not try to dissect the process and come up with mechanistic or phenomenological explanation of each of these parts. We take the whole process as what we may call as a unity or as a box, I may say. So we take this process and we just divide the variables into two. The variables that we are going to use in predicting the quality variables are called regressors or predictors. So what did I mean by that? Actually, what we are going to do is we would like to predict the melt index and polymer yield rate here. These are going to be our quality variables. In statistics, these are called response variables or dependent variables. I'm going to be using all of them interchangeably, right? In statistics, again, these are going to be called melt index and polymer. Of course, I'm talking about within the context of this study here. The variables that we would like to predict, that we would like to come up with a model with, are going to be called response variables or dependent variables. When it comes to chemical engineering, these are usually called quality variables. So quality, we are trying to come up with a model of quality variables in terms of not all these very complicated mathematical models which tries to explain every smaller dissected part or the region of the whole process, but we are just taking measurement from the process. So the variables here probably correspond to catalysis. I haven't read the whole thing thoroughly, but it is not very much important. T is temperature, P is pressure, L maybe I don't know. We have to check what L is. It may be maybe length of something, but these are the variables which are going to change during the process. So, and they are easy to measure. So what we do is we take measurements of these what we call process variables, and we try to come up with, or we try to associate the quality variables to those process variables. And those process variables are going to be called regressors or predictors or covariates in statistics or independent variables. So what we are going to do is we are going to come up with a model of dependent variables in terms of independent variables. It's that much easy. Compared to the other case, you may say that didn't we have all these variables here? For instance, it says and C2. We may have, but the thing is that probably we had so many more of these variables also. It doesn't matter that we should have all these variables here that we measure for producing an empirical model and for producing an fundamental or a constitutive equation or a phenomenological model. They do not need to be identical. But in order to come up with a concrete phenomenological model, you have to be you have to have a very strict, you have to have very deep information about each fundamental unit. so that you can put all of these fundamental units, you can combine all of them and come up with a model that is realistic enough that you can use. In empirical models, you don't need to do that. You don't need to understand the inherent structure or the working mechanism, what's going on here. You just would like to relate some observed measured variables to some quality variables. So this is the issue at hand. So when we go back to our PowerPoint slide, here in statistical modeling paradigm, what we assume is that the process under study produces data according to a joint probability distribution of Pxy. So what do I mean by that? Here, X will correspond to the regressors, predictor variables, or in terms of chemical engineering, they are going to be process variables, and Y will correspond to, there should be, of course, a comma here, Y is going to correspond to the quality variable, or in statistics, they are going to be response variables or dependent variables. There's going to be joint probability density here between those two sets of variables. And we would like to predict this one using the experiments at hand. And here note that these regressors will be X, and the response variable, at least one response variable, I may say, you may have more of them, is Y. So what we need to predict is this joint distribution. On the other hand, finding this joint distribution is a little bit of a pretty much difficult task. You should have a very large amount of data for that. And actually, practically, in many cases, we may not need that joint distribution. Instead of that, what we are much more interested in may be to obtain or to estimate a conditional distribution of this one. Now, let's remember what conditional distribution means. Given the values of X values, what were the X values? There were regressors or predictors. In terms of the process, they correspond to the operating temperature, pressure, the amount of C1, C2, whatever these corresponds to, the amount of catalyst put at the very beginning. You give these values, and corresponding to these values, let's say we are given these values, give me or predict me the quality variable. What was the quality variable? The melt index, for instance. Give me a prediction for that. This is that type of a model. In many circumstances, that type of a model is sufficient for our purposes. Actually, that model, again, in many cases of those many cases, the most important thing that we need is not maybe even the probability distribution, but it is only the expected value. So given those X values, give me a prediction for Y, where this corresponds to the prediction of the Y value. So what we are interested in would be Y hat given at some X values. So under these operating conditions, what is the corresponding quality variable value? When regressors are equal to those variables X, what is the response variable equal to? In terms of statistics, the first way of explaining the whole thing was in terms of a process engineer. As you have probably realized, I try to give you both the process engineering view and terminology, and statistics view and terminology. Anyway, so can we come up with, so we are not going to be dealing with that. That's a too difficult question, but we are going to be dealing with this. And more importantly, even we are going to be dealing with this. But as you are going to see for the linear regression case that I'm going to be talking about, these two will be pretty much connected. But here, the most important question is this one. Given the predictor values, can we determine an estimate for the response variable? Okay, so in statistics, what we do is something like this. Now, compared to mechanistic modeling, now in this case, we don't try to or aim to understand each individual piece or the working mechanism thing as a whole. Instead of that, we know that we can measure some variables and we would like to estimate a specific quality variable. So we assume that the relation between those two, there is a functional relation with these two, and the function f is unknown. So when x values are given here, this function maps this to a y value, but unfortunately this is clouded by what we call random noise. Usually we, or random error, usually we assume this random error to be independent and identically distributed, and we are going to be furthermore consider this or take this as a normal distributed random variable. But let me repeat again, what we assume as opposed to mechanistic modeling, where you need to write every equation in detail, what we do here is that we assume that there is a functional relationship between the measured variables and the important quality variable, response variable, or the dependent variable that we are going to use for our purposes. And this relation is actually deterministic. Here, this f is a deterministic function, but actually some stochastic or statistical, a random error term here is a random variable. So since error is a random variable, y also becomes a random variable. So y is going to be composed of two parts, a statistical part and also a deterministic part. So here what we would like to do is we would like to estimate this f here, and we are going to call it f hat. So from actually, if we go back here, remember, to construct a statistical model, we need some observations, a set of statistical units here. This is the formal definition, but actually we need some experiments, and we need to collect xy values, x and y values listed in this fashion. Well, actually, you should realize that we may have many of these x values. For instance, in this paper, we had, I think, the catalyst amount, the temperature, pressure, but within the scope of this course, I'm going to only concentrate on a single x. Here's what you may have different predictor variables, not only a single one. Anyway, so, but having this table at hand, what we are going to do is, or what we would like to do is to estimate this f value. So note that I have not described, I have not parameterized this f yet. So the simplest, but also probably the most useful and the most generally used parameterized regression function f is what we call first order linear regression model of this type. So this we may assume that, and this regression function will work for a surprisingly large number of cases, is going to be equal to a linear function of x. And the parameters here will be a slope function beta 1 and an intercept beta 0. So actually, we can, when we take this fx as this one, so when you put it here, this fx here, these terms here, y is going to be equal to beta 0, beta 1x plus random error. So given a certain process operating condition, temperature, whatever, or in statistical terms, given the independent or covariate or predictor variable, note that this is going to be multiplied by the parameter beta 1, added beta 0, and this is going to correspond to the deterministic part of y. There's going to be a random error term, which we are not going to be able to predict or estimate exactly, but we are going to be talking about its properties in a couple of minutes. Then we are going to end up with y value. So the deterministic part plus a statistical part is going to end up with the random, with the quality variable or the dependent variable y. Well, you may ask, why did we assume this one? Actually, you can, if you like, you can increase the order here in this fashion. If I'm going to be still talking about a single predictor here, right? You can increase the order as much as you like, but there is going to be problems related with that. So that's why we prefer this model. There are other nonlinear functions of x you may add. For instance, you may add logarithm, then you may say beta 3 sine x. There are things like those, but which are all out of scope of this course. And if you have more than one predictor, let's say this is x1, you have also x2, so you can also add x2 here in this fashion. So we use linear regression model. Well, one reason is because it's simple to handle, but the simplicity also brings some statistical advantages, which I'm not consider within the scope of this lecture, but in the next semester, when we are talking about the hopefully the chemical layer engineering laboratory unit operations, I'm going to talk about more why the advantage of linear or first order linear models compared to quadratic or other models. Of course, you may have also nonlinear models. So a nonlinear model would be something like this: beta 1 x over beta 3 square root of x beta 4 x to the power 2, for instance. I just made that. So here, actually, linearity does not correspond to the linearity of x. If it were, that wouldn't be a linear function. Note that this is still a linear, but a second order linear function. But linearity is totally related with the parameters here. This function is a nonlinear function with respect to its parameters. I think that's sufficient. Anyway, so this is what we call a statistical model relating x to y. And this is going to be one measured variable, for instance, temperature, and this is going to be the melt index, some polymer quality. Now, this is a very simple equation, as you can see, but it may seem strange. But in many instances, those very simple equations might be as successful or even more accurate in predicting the y values compared to phenomenological or fundamental models. Okay, now let's talk about the statistical properties of this, what we call statistical model. Now, we are going to assume that, and this is going to be this assumption will be maintained for the rest of this lecture. We are going to assume that random error term is zero mean sigma square distribute, normal distributed random variable. Now, sigma square is just to give a variance to that random error term. What do I make of zero mean? Now, if you think of this error as, for instance, measurement error, while there are different ways of talking about this, it doesn't need to be always measurement error. It may be all the sum of all the uncontrollable nuisance factor affecting on the system. But the moral of the story is to make it much more easier to grasp. If you think about, call it a measurement error. So this part gives us the relation of the process itself, of the machinery, but the y value that I obtained is due to some measurements, some readings, some errors during those readings. Now, if you think about that, it is pretty much straightforward to assume that those readings may be both on the positive and on the negative side. So there is no directional preference related with that. So in this case, zero mean of random error seems pretty much plausible. Now, from a more, like we say, serious statistical perspective, you may consider also that one. If error is assumed to be around some, let's say, a value of b, then hopefully you can take this b and take it into this parameter beta 0 here. Always you can do that. How are we going to do that? When you take the expected value, let's actually apply this, but let's first assume this, then see that this is going to be the case. Then I'm going to talk about taking a non-zero mean expected value. Anyway, now for this equation, if we take the expected value here, but I'm going to take the expected value given some x value. Why do I talk about that? Because as you have seen and I have talked about here, I'm not going to consider this case. I'm not interested in the variation of x. I'm more interested in the case that x is given to us, the temperature of the reactor is this one, what is going to be the related melt index value or quality variable value. So I don't want to go into statistics related with x. And there's going to be another issue I'm going to talk about when it comes to linear regression. And you are going to see that. Let me give you the hint. It may be a little surprising, but x will not be a random variable. But at this point, let's not talk about that. Just using x as a given value is sufficient. So when x is a given value, then the expected value of y is going to be equal to, this is a constant, beta 1 is a constant. Now, since x is now given, it's going to be another constant, it doesn't have an expected value. So is this going to be when you apply expected operator here? These are going to be the specific value of x instead of this one, expected value of random error. When we take this to be equal to 0, the expected value of y given x is going to be equal to this expression. Now, if this were not equal to 0 but equal to this one, then expected value of y given x would be equal to beta 1 x plus b. Then for this case, I would have defined a new beta 0, call this beta 0 prime, which would be equal to beta 0 plus b. So when I do that, actually, now the new model would look in this fashion. Y is equal to beta 0 hat plus beta 1 x plus error. Now when you take the expected value, since this is going to be equal to expected value x beta 0 at beta 1 x plus, let's also call this error prime. There's a reason for that, error prime here. Now to make those two equal to each other, note that this beta 0 is beta 0 prime is already equal to beta 0 plus b. So this term corresponds to these two, and beta 1 x here. So the expected value of E prime is going to be equal to 0. So what I'm trying to say that if we have a random error term given in this fashion, you can always convert the question into a fashion such that we are going to have another random error term with 0 mean and sigma square variance, and the intercept, that additional bias term in the random error term, you can add this to the intercept. That's just for the curious souls. That much detail, of course, out of the scope of this course, not required. But basically, this expectation operator. So we are going to be using this random error term here. Then this is going to be expectation of x. Oh, y, I'm sorry. So what does it say? Simply take the x value, multiply it by beta 1, add beta 0. This is going to be your expected value. And we are going to also show that in the next lecture, this is going to be also the best estimate of y. And when we take the variance of both sides here, apply variance operator, 0 variance, this is both going to be constant because these are at x. So beta 1 times x is constant, variance is equal to 0. This is variance of E. So variance of y given x is equal to sigma square. So the variable that we would like to measure, our quality variable, will be around a beta 0 plus beta 1 x value, and it's going to have a variance of sigma square. And note that, last of all, since this is going to be a constant, simply given some x value, and E is normal distributed, this is going to be a linear combination or linear function of a normal distributed random variable. Therefore, y given x will have that distribution. Its mean is going to be equal to this quantity. Its variance is going to be equal to the variance of sigma square. Very straightforward thing. So we have step by step, we have gone into the very first and the simplest statistical model, or what we may call empirical model. Now the important point here, what we call model parameters are going to be beta 0, beta 1, and sigma square. Note that x0 is not a model parameter because it's not a construct of, or it's not a constant of the model. X is going to change depending on the experiment, depending on the measurement. For a different temperature reading, we may predict a different quality value. But these are going to be constants, but they are going to be unknowns. They are just going to be like mu and sigma square of population parameters that we have considered previously, but I'm going to show it next. So please be patient. So when we perform a set of experiments and we obtain this data, note that this is how I denote it. This is a very typical representation, especially used in machine learning. Xi and yi couples. I is from 1 to n. These denote the each of these data points, so each of experiments, n experiments, and from each of the experiments, we take a couple of readings, x and y. So having that at hand, we are going to be somehow using that data to come up with the estimates of these parameters. So when we estimate these 3 parameters, the mathematical model of this mathematical model will be obtained or will be totally determined. So when I say this, we call example, we estimate the model parameters. This is very similar to we collect the data, and we estimate the population parameters. So one may ask, what is the relation between what we have done up to this point in terms of random variables and t-distributions, chi-square distribution, or hypothesis test, and these statistical models? The idea is going to be very interesting. We can equivalently show the very same random variable, all the random variables that we have covered, in a statistical model representation. What do I mean by that? For instance, that was a question we previously solved, the daily arsenic concentration in a region. I think the question was about comparison of two regions, but let's concentrate on a single one. And let's call this the daily arsenic concentration in a certain region. Let's name this random variable y here, not x, so that it's going to be easier to see the relation. And in those questions, we always say that, and we say it again here, y is normal distributed. So this arsenic concentration day to day, with population parameter, population mean, mu, and sigma square. Then what we did was y is normal distributed with population mean and sigma squared. This notation. Then we continue, we take a sample, y bar is also normal distributed with mu and sigma square over n. Then y bar minus mu is equal to whatever it got. It all went like that. Actually, I never talked about something called a statistical model. We didn't bother going into the concept of statistical model, but we can actually show this, or we can represent the whole story also in this manner. Why the arsenic daily concentration is equal to a constant value. Call it anything that you like. If it's not a beta zero, call it K. I don't know. But I just called it beta zero so that you can see the relation. Plus, so this is a constant term, which we do not know, plus some random error term. And this random error term is normal distributed with zero mean and sigma square variance. Now, believe it or not, this statistical model is totally equivalent to this representation. So let's see that it is. So note that the model parameters here are going to be equal to beta zero, and since E is a statistical quantity, sigma zero. Well, we force E to have zero mean, and I try to explain why, because it's not zero mean. You can always put the residual or the bias here in the intercept here, so no big deal. So just determining or specifying sigma square value and beta zero value, you say everything you have to say about Y. And let's see that that whole model will give us the very same information that we have used, or that we have the nomenclature or the representation that we used previously are identical to this statistical model representation. Now, let's take this one. Take the expected value of both sides. So when you take the expected value, this is going to be expected value of beta zero is going to be equal to simply beta zero, because it's a constant. And expected value of error is, since it is equal to zero, it's going to be like this. So expected value of y, which is actually equal to mu, is what we call beta zero. So think about in this way: old method, new method. What we call mu in the old method is actually equal to beta zero in the new method. Of course, this old and new is with respect to the order that I'm trying to explain the things. So this new is what we call the statistical model or modeling approach, whereas this old one is take a random variable, describe its distribution. Okay, and when I take the variance of both sides, variance of y is going to be equal to some constant plus error is going to be equal to variance of error is going to be equal to sigma square. So basically, sigma square in the old model or the old representation is going to be also sigma square in the new representation. And therefore, actually note that since this is a constant, right, and this is a normal random variable, therefore a linear combination, linear function of a normal random variable is normal. Y is going to be normal distributed with n and with mu and sigma square parameters, and this is going to be exactly equal to this. So I repeat again, what I have shown here is that if you start with statistical model, you end up with the random variable that we have defined at the very beginning. So what's the advantage of using this statistical model? First, if you are a newcomer to this topic, there is not a this not an advantage. It seems a bit confusing. That's why we talked about single random variables and their distributions. On the other hand, if you're a little warm up with those statistics, this is actually a much more a more informative representation. What do I mean by that? This means this equation, or the way that we see that we read this model is by this way. The daily arsenic concentration here fluctuates around a constant value, beta zero, which we do not know. But as I said, it fluctuates, and the width of the fluctuations is proportional to that sigma value here. So that is going to be like this. So there is that area, let's say there's a lake here. The nature and all these conditions, or the deterministic part, determines that beta zero value. And it's a constant every day. On the other hand, from day to day, there are other unseen factors or undetected, uncontrollable nuisance factors that affects the y value, which changes with this distribution. So it is superimposed. You may call it, we may see it that way actually. There is beta zero coming here from the nature, and also this error. These two are superimposed, or let's put it that way, they are added on top of each other. This is actually a process control representation, and the result is going to be what we call y. This beta zero is due to the deterministic part, and this error is due to the stochastic part, which changes day to day. So this is the idea. Now, compared to the previous case, the only difference is that this expression does not cannot be seen here. So there is no beta 1 x term. So what does that mean? Actually, there is no x here. That's probably what it means at first sight. So, but actually there is a much more deeper meaning than that. What does it mean? There is no x here. There is no regressor. There is no measurement. Actually, maybe you haven't taken any other measurement, but there are many things that you could have measured. For instance, you could have taken temperature measurement. You could have taken, I don't know, the wind, the velocity of the wind measurement, whether it's clouded that day. There are many other measurements that you could have taken, but you didn't take them. So one way of thinking about this is all the possible x or the regressor values which possibly significantly affect this y, they are at constant values. So think about it that way again. There is a very important variable. Let's say that they are the temperature measurements. But if the temperature measurements do not change within, let's say, 10 or 20 Celsius, they are not going to have an effect. So when the temperature changes, let's say a temperature change from 30 to 35 is no big deal. It seems as if no change here. So this is why, if there is really a relation in this way, and the temperature changes during all that seasons that we take measurements, if they are very small or there is no temperature change here, x is going to be a constant. When this is constant, multiply by beta 1 and add beta 1, this is going to be totally another constant. So actually, the model that we are going to be including, this beta 0, also includes all the constant regressor values during those observations. So it is the meaning of the intercept. That's an interesting thing here. So why is that there? It is all the effects that do not change from experiment to experiment. Whereas the second beta 1 is there are changes in x values, and these are going to be multiplied or magnified by a factor of beta 1. This is called actually a partial effect. And this is going to be superimposed on beta 0, which is due to the all the constant effects. And this is going to determine, or we are going to be determining the deterministic part, finding the deterministic part of the equation. And this error part, as I said, maybe the simplest case may be due to measurement error, but there are also the cases that there are many other variables changing occasionally. So there are going to be effects of these nuisance factors. So anyway, as I tried to, I hope I was able to show you, actually, it is possible to show to represent all the calculations, all the random variable representations that we have covered up to this point as a statistical model in this fashion. A constant plus a random error, and the random error has a normal distribution with zero mean and sigma square variance, where sigma square is going to be the same variance of y, and that constant is going to correspond to mu. If you like, you can model it also in this perspective, or expected value of y plus error, random error with that much sigma square. In this chapter, on the other hand, we are going to be introducing another variable x, a regressor, that this is going to change from experiment to experiment. Therefore, we would be interested also in this beta 1 value. And we are going to be talking about the parameters beta 0, beta 1, and sigma square, and they are going to be very similar. So actually, they are going to be not very similar, but they are going to be the population parameters. The only thing that's make this unlike the populations that we have seen is this time this population here, this population of y, the distribution of y will depend on the given x value. Given an x value, there's going to be a constant distribution of y around this mean and this sigma square value. That's why we need to determine all of these parameters.